Hello friends, welcome back to this course on combustion in air-breathing aero engines. So as you have seen that we have covered quite a bit of ground so far. We have talked about kinetics, we have talked about chemical equilibrium, we have talked about kinetics, oxidation mechanism of fuels, then we have looked into transport phenomena, and then we looked into the governing equations. And after that we went to basically the formulations for non-premix flames, and then we looked into a very ideal kind of a non-premix flame, which is a chambered flame, and then we looked into the droplet evaporation and droplet combustion, which is also an example of a non-premix combustion. Okay. Now then of course we have said that in nature or by design, fuel and oxidizers are separate, and then of course when the meet because of diffusion and because of the continuous consumption of this oxidizer and the fuel by the flame, then a non-premix flame is actually formed. Okay. The non-premix flame, the issue is that in the non-premix flame the fuel and the oxidizer are not mixed at the molecular level a priori, and they only meet at the flame location itself, and where they basically burn in stoichiometric proportions, and as a result the flame temperature that is formed is the adiabatic flame temperature, and which is also the reason why non-premix flames produces a lot of pollutions in terms of NOx, soot, etc. Okay. So those we have discussed about non-premix flame. We have discussed plenty about droplet, about condensed matter evaporation, and then into droplet evaporation and droplet combustion. Also, but as you know that there is another variant of flames, in another mode combustion can happen, of course, and that is in premixed mode. Okay. So in the premixed mode, the fuel and the oxidizer, okay, they are mixed at a molecular level. They are perfectly mixed before combustion happens. Okay. And this is different from the non-premix combustion. There are quite a few differences with respect to non-premix combustion, but you will see that there are also quite a few similarities. That is, both essentially we will see that there is another in flames, that is premix flames that we will talk about. Those are also very strongly controlled by diffusion. So it is to be borne in mind that both the non-premix flame as well as the premix flame, they both are in both processes diffusion plays a very important role, and we need to understand that very well. And then so next we go into this into this course, in today's class, where we will talk about laminar premix flames, and here we will see that these are the topics that we will cover. We will cover this Rankine-Hugoniot relations, and you will see that these basically talk about how the thermodynamic properties and in the burnt and the unburnt gases can be connected by this sort of relations, and very interesting properties of this of the different types of the modes of premix combustion that can happen emerges from this kind of analysis. And then we will go into the laminar flame speeds, which is the most important property of a premix flame, and we will go into different levels of derivation, where we will do a phenomenological analysis just to give you an idea about what are the processes that are important, and then we will go into the chemical structure of the flames. Okay. So premix flames, as you see that, though it is, as we have discussed previously, that that when we compare, we always compare premix flames with non-premix flames in terms of the properties and the advantages they have, and you will see that unlike non-premix flames, in the premix flames one can readily control the temperature by just controlling the equivalence ratio, and that gives an advantage because this allows you to have low temperature, not very low temperature, but still lower than the non-premix flame temperatures one can achieve, and one can design the combustion process accordingly. But then there are other challenges with the premix flame, because you will see later that the premix flame is essentially a wave phenomena, and so you need to basically control the wave and to do some design in the combustor to have its proper to basically stabilize the wave. Okay. So there are very interesting features that emerges from the premix flame. So sometimes to control over to have a control nowadays in inner propulsion engines, many of the engines try to go towards a more and more premix mode from the non-premix mode, because as I have said earlier that the premix mode allows you to have better control over to lower essentially the emissions NOx emissions, soot emissions, these can be much lower in case of premix combustion with respect to those in non-premix combustion. So for that it's very important to know premix combustion, and as I said that even modern gas turbine engines, like previous generation gas turbine engines were very strongly non-premixed. Okay, so but the modern generation gas turbine engines, for example the GE-NX engine that powers a Boeing 787, as you know, that those use this twin annular premix swirler combustors. Okay, so this combustion happens in a partially premix mode. So the idea is that from non-premix we are trying to go to more towards premix to basically have a control over the emissions. So it is important to first understand that why basically you can have a control over the emissions when you do premix combustion. So we will take those things in this class, and we will also do appropriate comparisons with the non-premix flames to basically understand it. But of course it must be borne in mind that this in a combustor, in an actual combustor, it's not a laminar premix flames that we encounter. These are very strongly turbulent premix flames that we encounter. But as you know that to understand something very complex you need to understand the basics first. Okay, so that is why we will go deep into this discussions on non-laminar premix flames, because only when you understand laminar premix flames we will be in a position to understand turbulent premix flames, and which is what happens inside modern or postmodern combustors that we encounter or will continue to encounter in some few years to come. So as I said that here we will discuss the 1D wave structures of premixtures. Okay, so as we have seen that non-premix flame is basically diffusion controlled, because we can assume that the reaction is much faster than the diffusion, and it is of course diffusion control, and we have seen that the flame stabilizes in the location where it is essentially the fuel and the oxidizer are essentially in the stoichiometric proportions, and the temperature achieved is essentially at is the adiabatic flame temperature for the corresponding stoichiometric mixture. Okay, and so essentially it is a non-premix flame is purely controlled by diffusion, and it is essentially it happens in subsonic flows. Okay, now premixture, when you have a premixture, that is when you mix the fuel and the oxidizer, say when you mix methane with air or you mix hydrogen with air, okay, so it can then readily react. All right. Now once you ignite at a point, then basically what happens is that a chemical wave, which is essentially the flame or which is essentially, as you will see later, this either a deflagration or a detonation depending on its speed, a chemical wave is formed and that propagates through the mixture, converting into product. So if you have a tube like if you have a long tube, if you have a tube like this, or if you have a long tube like this, and this is filled with if this is entire tube is say this is closed here, and this entire tube is filled with fuel air mixture, and then you ignite at this point. Okay, so then immediately a flame will be formed, and it can be of course in different shapes, but anyways in an ideal version it will be a laminar flame will form, and this will propagate onto this until the entire mixture is consumed. So essentially it is a wave structure that is propagating through this entire tube, and so as you will see that one of the basic descriptions of a premix flame is basically its wave phenomena. Okay, so the propagation rate, unlike as we have seen previously in the non-premix flame, the propagation, the burning flux of or the burning rate, the burning flux F, that was proportional to basically the thermal diffusivity. So it's essentially was purely diffusion control, but here you will see that the reaction rates plays a very important role. All right, so here it is, you will see that basically it will emerge very clearly that in the premix flame both the diffusion and the reaction processes are equally important. Okay, so when the reaction rate becomes very important, then of course you cannot assume that it is infinite with comparison to the diffusions, and then you have to basically consider the detailed reaction rates. You might have to consider detailed reaction rates. Of course a lot can be understood by considering the one step reaction rates also, and this is because it is a wave phenomena, it can either be subsonic or supersonic, and the subsonic state will be essentially called deflagration and the supersonic state will be called detonation. Okay. Now first we will in this we will go into this first description, that is the Rankine-Hickenauer relations, and what this does is basically you have if you have a premix flame, the flame as you know, because of the large activation energy, is confined into a very thin region. So, upstream of the flame and downstream of the flame, these are, there is no reaction happening, okay, because reaction is confined in a very thin region. So, upstream of the flame is of course reactants, that is the fuel and the oxidizer mixture. The downstream of the flame is of course the bond products, and both are essentially in the down is in chemical is in an equilibrium state, okay. So we can assume that equilibrium state exists in the far upstream and downstream of the wave, and we will not consider in the first level description in this Rankine-Hugoniot analysis. So, we will not consider this will not consider this non-equilibrium process of diffusion reaction within the wave, and as a result of that we will see that the wave speed will not be specified, but then we will just try to somehow relate the downstream state of the wave with respect to the properties of the upstream state of the wave and vice versa. And of course, that will not give, unless it is a very special case, I will say, as we will see, that the wave speed will not be specified. So, you still, to close the problem, you have to specify the wave speed, but then without that, as long as that is specified, we can relate, we will see that we can relate the downstream state and the upstream state of the wave in a very comprehensive manner, just by using the very basic governing equations of mass conservation, momentum conservation, energy conservation, and where we do not have to consider details of the chemical kinetics, because we are not essentially interested into the wave structure. The wave structure is essentially controlled by kinetics and diffusion processes, but whatever happens far upstream and far downstream, as you know, the far downstream, it is essentially in equilibrium state, and that is given by equilibrium relation. So, you do not need chemical kinetics to basically know that. So, you will see that this solutions of this kind of an analysis will give you two branches. One will give you a subsonic deflagration and wave, and another will give you a this is a subsonic deflagration wave, and another will give you a supersonic detonation wave. Okay. Now, the wave speed will be, as I said, that we will be analyzing, will be obtained by analyzing the wave structure, and that is basically wave speed means the flame speed, and that will come later. So, for now we will not consider the flame speed, and we will consider this very idealized description that is shown here. Okay. So, what does it say? It says that if we consider this premix flame or this wave, which we consider to be in a stationary state with respect to the our laboratory coordinates, then that, if that is so, then of course it has to be, to sustain that structure in a steady state, of course it has to be fed by premix reactants, and these premix reactants are being fed into the wave at a velocity uu, and the Barn products and the premix reactants of course are converted into Barn products in this wave structure, which we are not specifying here, and this the velocity of the burnt gases is essentially ub. So, similarly, the properties upstream of this wave is given by rho u, pu and tu, where subscript u means unburnt, whereas the properties downstream, that is in the burnt state, is given by the rho b, pb and tb. Okay. So, these are the different states of the upstream state and the downstream state of the unburnt state and the burnt state of the wave, and what our objective in this analysis would be to have relation between them and between the upstream state and the downstream state, and we will not consider the wave structure. But as I have said, that the problem will not be complete without specifying the wave velocity, and for that needs will be put in as an external parameter, all right, which should be specified by something else, which we will not consider here. We will consider that is to be given for this problem. Okay. So, how do we arrive at this? How do we relate the upstream and the downstream states which are in equilibrium of this wave? For that, of course, as you know, in any problem, fluid mechanics, essentially reacting fluid mechanics, though we are not considering reactions here. So, here where there is some change of state happening in terms of that is the reactants going into products. So, of course, mass is conserved. So, then if you write the continuity equation and you integrate that from upstream to downstream, this is what you will find, that rho u uu times rho u uu is equal to, that is the density of upstream times velocity of upstream is equal to density downstream, or the density of the bound state times the velocity of the bound state, and this is equal to F, which is the mass flux. Okay, it is not the mass flow rate, it is the mass flux, and we will also call this as a burning flux, because this is the flux which is being burnt and converted into products. And then of course the momentum, so this is your this is the momentum, the axial, which is once again, as you see that this analysis is in purely in 1D. So, we can basically, if we, what we can do is that we can take the complicated momentum equations and then we can just integrate around. So, then this is what you will get. So this is what you get by integrating the acceleration terms, and this is what you get by integrating the pressure gradient terms along the one dimension. So this is you get rho u times u square plus pu is equal to rho b times ub square plus pb. So this is what you get. We can just simply show this by considering the 1D momentum equation, of course in a steady state, that is this was the momentum equation if you remember, is equal to minus dp dx. So if you integrate between xu and xb dx, and you will get is essentially, and of course the rho is here, and you will get, and we can just write rho u to be essentially f. So f is constant, so it comes out, so f times u, so fu uu minus, or fb ub minus fu uu is equal to minus pb minus pu. So fp is nothing but rho u uu, so you find that, or we can write as rho b ub, so you find that rho b ub square minus rho u uu square is equal to minus pb minus pu, and this implies rho u uu square plus pu is equal to rho b ub square plus pb. So this is exactly what you get. Okay, so we will not of course here we are this is just to show that if you consider the 1D equations in the differential form, in the PDEs we convert that to basically we convert that to ODEs, because there is no time variation, there is no variation in y and z, so it's only in x variation, and then you can just write down these things, which is which is the momentum equation in the integrated momentum equation in x directions. So this is it, and then the energy equation is, of course you have the enthalpy, the HU, and then you have, which is the internal energy plus PV, where V is the specific volume here. So and then you have the kinetic energy term, and then you have the burnt gas enthalpy, and then you have the burnt gas velocity. Of course you have to remember that this HU and HB are total enthalpies, and even though there is reaction happening, the total enthalpy is conserved, because what happens is that the enthalpy of formation is converted to sensible enthalpy as combustion happens. So this individually this contains the enthalpy of formation and the enthalpy of, and the sensible enthalpy. Okay, so now you can get by, if you use these two things, okay, if you use the mass and the momentum equations together, okay, so if you combine them, then you basically get something like this, that is Pb minus Pu is equal to, if you just consider the momentum equations, this is just given by, if you just take the rho u times u square, and then you of course have leftover rho b and rho u in the denominator, but then using the mass conservation equation you can substitute rho u is equal to, of course this is also obtained by mass conservation equation, so and you can of course substitute this, and you get Vb minus Vu, which are the specific volumes. Okay, so these are the specific volumes and should not be considered with velocity. And then of course if you write that that sound speed is equal to root over gamma RT, and then you do this manipulations, you will find that mu square, okay, so mu square is nothing but, mu is nothing but the Mach number at the unburned gas, which is nothing but u times c, okay, and this u times cu, and this mb is nothing but u times cb, that is the ratio of the velocity to the acoustic velocity to the acoustic speed, and then you can write this equation. Okay, so this gives you, when you combine the mass and the momentum, it gives a very interesting thing. So it gives you that mu square, there is a Mach number square, is essentially equal to p cap, whereas p cap is nothing but P cap is nothing but P by Pu, and V cap is nothing but V by Vu, that is with respect to unburned gas. And of course here the P cap is not P by Pu, P cap is essentially the ratio of P cap is equal to Pu by Pb, and V cap is essentially V P cap is equal to PB by PU, and V cap is equal to VB by VU. So P cap is essentially the ratio of the gas of the pressure at the burned gas with respect to the pressure at the unburned gas, whereas V cap is the ratio of the specific volume in the burned gas with respect to the specific volume in the unburned gas. And similarly, the whereas this mu is nothing but is equal to nothing but mu is equal to U by Cu, which is the acoustic velocity. Cu is equal to root over gamma T. Okay. So similarly, so you can write both in terms of in terms of so here is what we wanted, that is we wanted to relate the ratio, the burned gas state to the unburned gas. We wanted to relate the two states, that is a burned gas state to the unburned gas state in terms of the thermodynamic properties of the burned gas state to the thermodynamic properties of the unburned gas state. So this is the ratio of the burned gas pressure to the unburned gas pressure minus 1 divided by gamma times the specific volume of the burned gas with respect to the specific volume of the unburned gas minus 1 is given by mu square. Similarly, this is also given by mb square. So what does this tell you? This tells you a very interesting thing, that of course these are essentially straight lines which pass through 1 1, where P cap is equal to 1, V cap is equal to 1, and you see this mu square is essentially always a positive quantity because it is a squared. So minus gamma m squared is essentially the slope of these straight lines P cap minus 1 and V cap minus 1. Okay. So and because this is always positive, the slope of these lines are always negative. And also we have to see that another thing is that because we can write P cap minus 1 is equal to minus gamma mu square V cap minus 1. As I said, that P cap is the ratio of PB by PU, V cap is the ratio of VB by VU. Okay. And as such, as a result of, because P cap minus 1 is equal to minus gamma mu square V cap minus 1, and this is essentially always positive, so and this thing is always negative. So it means that when this is positive, this has to be negative, or when this is negative, this has to be positive. Okay. So that means that if P cap is greater than 1, V cap has to be less than 1. That means that when V cap is essentially the specific volume which is inverse of density. So it means that when P cap is greater than 1, the density ratio is also greater than 1. That is, when the pressure ratio between the burned and the unburned gas is greater than 1, the density ratio is also greater than 1. And you will see that this corresponds to later to the detonation stage. Okay, where the pressure and density both increase by crossing the wave. Okay, I am not calling it a flame, because detonation is not essentially a flame. A flame is essentially subsonic structure. Okay, so crossing that chemical wave, your peak pressure ratio and density ratio both increase. Okay, whereas in this case, you see P cap is less than 1, V cap is greater than 1. That means pressure ratio is less than 1, density ratio is less than 1, and that is your deflagration state, where both the pressure and the density drops by crossing the chemical wave. Okay. So now we can go into another set of lines, because you see we had three conservation equations. We had the conservation equations of mass, momentum and energy. So using the mass and the momentum conservation equation, we have arrived at this Rayleigh lines, which are essentially straight lines, passing straight lines of where the variables are essentially P cap and V cap, but that is the variables are pressure ratio and specific volume ratio. So these are essentially, the Rayleigh lines are essentially straight lines that pass through P cap equal to 1, V cap equal to 1, and the slope of them are given by, of this set of lines are given by gamma mu square, where mu square is essentially the Mach number of the unburned gas, which is also can be ratio taken as a Mach number of the flame speed, because the rho uu is, we will see that is nothing but the flame speed. Okay, so but this is not specified, we do not know what mu is or what uu should be for the flame to be stabilized. That is why it is essentially the flame speed. And but we have found that interestingly something more we found is that when P cap is greater than 1, V cap must be less than 1, or when P cap is when pressure ratio is greater than 1, the density ratio also must be greater than 1, and when the pressure ratio is less than 1, the density ratio also less than 1. And we have stated that The first condition corresponds to your detonation state and the second condition corresponds to your deflagration state. Okay. But then as we have not used the another equation, that is, so far we have not used the energy equation. So, we can also use the energy equation in alone or in combination with the mass momentum and energy equation, with the mass of the momentum equations, and that is what we will do now. So, if you do that, we find that if you use the mass momentum and energy equations, we come up with the Hugonot lines, which is this, that is the enthalpy difference between the burnt and the unburned gas. Once again, this is the total enthalpy difference, this is nothing but half times V B plus Vu divided times Pb minus Pu. Now, of course, because these are the total enthalpy differences, now we can write them as we can write Hb essentially equal to Hb0 plus Hbs minus Hu0 minus Hus. Okay. And so, once you do that, you can essentially see, that the heat of combustion is essentially the enthalpy of formation of the products minus the reactants, and that is when from that you can basically get the heat of this heat release, the chemical heat release. Okay. So, which we have the definition of which we learned previously, that is, it's essentially the H0k times Wk times nu k double dash minus nu k dash divided by your with the reference species, that is Wf times molecular weight, Wf being the molecular weight times nu double dash minus nu f double dash minus nu f dash. So, that was your chemical heat release, or so that is, let us write it down here. This is essentially summation k is equal to 1 to n Hk0 Wk nu k double dash minus nu k divided by Wf times nu f double dashed minus nu f. Okay. So, this was what we had defined as chemical heat release, and then of course, we can relate the sensible enthalpy to the temperature using the specific heat ratio, that is Cp, and once we do that, we can write this. So, once we combine these two things, we can write that from here itself we can write that Hb minus Hu is equal to Qc times gamma by gamma minus 1 times Pb. This is of course by Pb by rho b is essentially RTV minus Pb by rho u is equal to RTu. So, from that, using the ideal gas state, we can go from directly from here to here, and then equating these two things together, we arrive at this Hugonot lines, which are nothing but these things. That is, look at this very carefully. I will not go into the derivation, but the formula needs to be examined very, very carefully. These are very important. So, we see that the pressure ratio P cap plus gamma minus 1 by gamma plus 1 times V cap, that is a specific volume ratio, minus gamma minus 1 by gamma plus 1 is essentially 4 gamma plus 1 plus Qc cap, which is this guy. Okay, and Qc cap means of course this thing, rho u by Pu times Qc times gamma minus 1 by gamma. So, what this is essentially, we can, it's in a hyperbolic form, that is hyperbolas are essentially you see xy is equal to constant. Okay. So, it is essentially in that form. So, with asymptotes, so you see the these things P cap plus this is, so it will generate lines like this, as you know, that whereas these asymptotes are given by these things. So, the asymptotes here are essentially this one, the asymptotes of P cap is essentially gamma minus 1 by gamma plus 1, that is this part, whereas asymptote of V cap is essentially gamma minus 1 by gamma plus 1, this is this thing. And now the thing is that we can also this equation, of course, we have derived for combustion, where we have essentially equated the burnt state with the unburnt state of combustion, but we can also have we can also reduce to a state where there is no combustion. So, what we have to do is that we just have to set this to be equal to 0. So, when we set this equal to 0, we find that this then this line passes to 1 1. So, if you remember that 1 1 was also the line through which the Rayleigh lines pass. So, when you don't have any combustion, so these two essentially intersect at these lines. So, we will see also that it will intersect somewhere else as well. So, this is what you get by combining the Rankine Hugonot and the Rayleigh lines. If you remember, the Rayleigh lines was given by this. P cap minus 1 is equal to gamma I mu square times V cap minus 1. Okay. So, this is the Rayleigh line, we will just only use the mu. Okay. Whereas the Hugoniot lines or Hugoniot curves are given by P cap plus gamma minus 1, sorry, it is not visible in that part. So, P cap plus gamma minus 1 by gamma plus 1 times V cap minus gamma minus 1 by gamma minus plus 1 is equal to 4 gamma by gamma plus 1 whole square plus 2 QC cap normalized chemical heat release times gamma minus 1 by gamma plus 1. Okay. So, we have seen that these Rayleigh lines basically are arrived from mass and momentum. Okay. Whereas these lines essentially arise from mass, momentum and energy. Conservation. Okay. The difference is that these, as you see, that these are essentially straight lines, okay, whereas these are essentially hyperbolas. So, these lines that you see in this thing, if you plot these lines in the P cap V cap diagram. So, this axis is essentially P cap and this axis is essentially V cap. This is a very, very important and fundamental diagram in combustion. So, we have to really go into this. V cap, this is the V cap axis, this is the P cap axis, and this is the 1 point. Okay. This is the point where P cap is equal to 1 and V cap is equal to 1. Okay. Now, these lines, if you plot these Rayleigh lines, these are these lines. Okay. And of course, it depends on the slope. So, as the mu changes, we do not know what mu is right now. So, we can have different sorts of these lines for different mu's like this, but all of them has to meet at P cap V cap is equal to 1. Okay. And also here, so this state, as you see, corresponds to large, this is this part corresponds to P cap greater than 1 and V cap less than 1. Whereas, you can also have another part, as you see, this part corresponds to P cap less than 1 and V cap greater than 1. Okay. So, as you will see that when P cap greater than 1, that is when the pressure rises, when pressure rises in the combustion gases, pressure rises in crossing the flame, we will call that a detonation. When pressure drops across a flame, we will call that deflagration. So, this part essentially corresponds to the deflagration and this part essentially corresponds to the detonation. Of course, there is nothing that is possible here because of the slope, because the negative nature of the slope. If it something comes in this part, then that will have a gamma mu square to be positive, and that is not possible. So, everything has a negative slope in these lines, all right. So, now these are the straight lines, and then we all can also plot these Hugoniot curves. Okay. So, which are basically these rectangular hyperbolas, which are these lines. Okay. And here you see that the parameter that changes, we do not have any Mach number square, but we have a QC. So, this is the point where QC equal to 0, then it intersects through the passes through the 1 1 curve, but then as you increase QC, this curve shifts in this side, all right. Now, of course, as you have seen that the previous one, the Rayleigh lines are given by mass and momentum conservation, whereas the Hugoniot curves are essentially given by given by your mass and energy conservation. So of course all three should be conserved simultaneously, and these two equations should hold simultaneously. So that where the points where these equations are simultaneously hold, that is the point of intersection of the straight lines, that is the Rayleigh lines, with these hyperbolas, that is the Hugoniot lines, those are basically our acceptable states of combustion that we can have. Okay. So that is the thing. So we need to find out the points of intersections of these straight lines and the hyperbolas.